Good morning. I am here today to discuss my seminar topic Deep Learning for Classification and Localization of COVID 19 Markers in Point of Care Lung Ultrasound. Table of Contents Introduction Literature Survey ICLUS Database Frame Based Score Prediction Video Level Score Aggregation Semantic Segmentation Result Analysis Conclusion and Future Work and Reference. Coming to the introduction part of deep learning has proved successful in medical imaging. In the wake of the recent COVID-19 pandemic, some work have started to investigate a deep learning based solution for the assisted diagnosis of these lung diseases. Extensive testing and diagnosis are great importance in order to effectively contain the pandemic. This paper discusses about a fully annotated versions of ICLS database, a novel deep architecture which permits to predict the score associated to a single LUS image. In this paper, we describe the use of deep learning to assist doctors to determine COVID-19 associated imaging patterns on point of care LUS image. A simple and lightweight approach based on Unionome to aggregate frame level predictions and estimate the score associated to a video sequence. Address the problems of automatic localization of pathological artifact, evaluating the performance, semantic segmentation methods derived from fully convolutional architecture. Finally, conduct an extensive evaluation of these methods on all the tasks, showing that accurate predictions and localization of COVID-19 imaging biomarkers can be achieved with the proposed solutions. The figure shows an overview of the different tasks considered in this work. First one is frame-based score prediction, second video-based score prediction, third frame-based segmentation. The first task consists of classifying each single frames of LES sequence into 1 or 4 levels disease severity defined by the scoring the system. And video level grading aims to predict a score for the entire frame sequence based on the sum scoring scale. Segmentation instead compares pixel level classification of the pathological artifact within each frame. Now, next we discussed literature survey. First one is review of artificial intelligence technique in imaging data acquisition, segmentation and diagnosis for COVID-19. Focused on detection of COVID-19 from just CT. And second one is InfraNet automatic COVID-19 lung infection segmentation from CT scan. Is a U-type network is used to regress a bounding box for each suspicious COVID-19 pneumonia regions on consecutive CT scans. Third one is a deep learning algorithm using CT images to screen for coronavirus diseases. In this technique, a threshold-based region proposal is first used to retrieve the regions of interest in the input scan. Now we discuss about ICLUS database. The Italian COVID-19 lung ultrasound database ICLUS-DB is used for training and testing of the system. It currently includes a total 277 lung ultrasound LUS videos from 35 patients corresponding to 58,924 frames. The data were acquired within different clinical centers in Italy and using variety of ultrasound scanners. Both linear and convex probes were used depending upon the necessities. Of the 35 patients, 70 were confirmed positive to COVID-19 by swab technique, means 49% are confirmed to COVID-19, and 4 were COVID-19 suspected, means 11%, and 40 were healthy and symptomless individuals. To evaluate the progression of the pathology, a 4-level scoring system was advised with the score ranging from 0 to 3. Score 0 indicate a healthy lung surface, score 1 indicate the first signs of abnormality, score 2 indicate a more advanced pathological state, score 3 indicate severe infection in the lung. Of the 58,924 length frame forming this dataset, 5,684 were labeled score 3, means 10% were labeled score 3, indicating the serves infections in this length, and 18,972 score 2, means 32 percentage indicate a more advanced pathological state. 14,295 score 1, means 24% indicate the first signs of abnormality, and 19,973 means score 0, means 34% indicate a healthy lung surface. The following figure illustrates the distribution of the subprobes and the scores of the frames grouped by the hospitals and overall statistics. Now we discuss about frame-based score predictions. The frame-based score prediction predict the presence or absence of the pathological artifact in each frames and automatically access the severity scores of the diseases. Spatial localization of pathological artifact in the frames without assuming any annotation about such artifact positions. The weak localization is achieved through the use of the spatial transformer network. The problem can be formalized as let X denote the input space. Let X denote the set of possible scores, and during the training, a training set T is equal to set of xn comma sn up to n is equal to 1 to n is given where xn element of x and xn element of capital. The system needs a learning a mapping phi from x to capital S. Phi is modeled as a composition of two functions. Phi is equal to phi of stn composition phi of cnn. Phi of stn is from input image space x to x, and phi of cnn is s to capital S. In this method, an input image x is processed by the phi of stn that predict two set of transformation theta 1 and theta 2. The transformations are applied to x generating image x1 and s2. The network phi of cnn is then applied to x1 and s2 producing two set of logits for the same image under different transformation. The phi of cnn of x1's branch is then trained with the any standard supervised classification laws, and phi of cnn of x1 comma phi of cnn of s2 is then trained. Ordinal regression is more appropriate way to predict labels from an ordinal scale. A lightweight approach for the soft ordinal regression (SORD) is used. The ground truth information is encoded in soft valued SORD vectors. S cap is equal to e raised to minus delta x comma I by sigma j element of x e raised to minus delta j comma I. At the training time, simply train the network phi using cross entropy LSORD. The LSORD is calculated by minus sigma I is equal to 0 to mod s xi cap log exponential of phi of x of I divided by exponential of j up to mod x exponential of phi of x of j. The consistency loss is defined on the network representation as LMSE. MSE means mean square error. The localization network is stimulated to produce reasonable scale patches by minimizing sigma minus sigma p, where sigma p is a fixed prior. In order to enable the STN into yield different parameters theta 1 not equal to theta 2, choose sigma p1 not equal to sigma p2. Hence, a loss is defined as follows: LP is equal to mod sigma 1 minus sigma p1 plus sigma 2 minus sigma p2. Finally, the proposed RAG-STN model means regressed STN model is trained end-to-end minimizing the following joint loss function. LTOT means L total is equal to LSORD plus LMSC plus LP. The ICLUS DB data set split into train set and test set. The test set comprises 80 videos from 11 patients with a total of 10,709 frames. All the frames from this remaining videos are included in the train set. The split is performed at patient level such that the set of patients in the training and test are equivalent. The following figure is the illustration of this architecture of frame-based score prediction. The following figure is an illustration of an architecture of frame-based score prediction. An STN modeled by phi of STN produced two transformations, that is theta 1 and theta 2, which are applied to the input image, producing two transformed versions x1 and s2 that localize pathological artifact. The feature extraction phi CNN is applied to x1 to generate the final prediction. The following figure illustrates a novel deep architecture which automatically predicts the pathological score associated to all frames of LUS images. Now we discuss about the topic video level score aggregation. In video level score aggregation, the frame based prediction should be turned into single video based score predictions in order to access the pathological state of patients. The video based score aggregation problem can be formalized as follows. Let V is equal to set of xi be a video, V be the set of videos of any length, and x the set of scores. The goal of the video level scoring prediction is learning a mapping sigma from V to S, and then the principle of mapping could be made could be obtained by taking the maximum score assigned to any frame of this current video, and then the hard rules however is one of this inapplicable in practice. And then inspired by this hard rule mentioned a simple strategy that combines frame level predictions using parameterized aggregation layer is proposed. Sigma of V is equal to sigma of U of phi of x1 up to phi of xm. Hence phi is the frame level mapping and U is the aggregation function based on uninorms, which is a principal way of soften the hard rule. A uninorm U is monotonic increasing commutative and associative mapping with the neutral element E element of 0, 1. This means that u of a comma e is equal to u of e comma a equal to a for all a element of 0 comma 1. U of a comma e is equal to u of e comma a. That shows the commutative property. And phi of v is equal to phi of u of phi of x1 plus x1 up to xn. If E is equal to 1, U is fully non-compensatory, like that taking the maximum between A and B, while it is fully compensatory if E is equal to 0, like taking maximum. Choosing E from 0, 1 allows the uninorm to have hybrid behavior. The appropriate value of the neutral element is learned from data. The aggregation layer takes as input the sequence of frame-based prediction score phi of x. Aggregation then using a uninorm U and return a soft value. Any uninorm with the neutral element E can be written as UE of A comma B. And then the function T and S are called T norm and T conorm respectively. Different choice for these functions leads to different uninorms. Min of A comma B less than or equal to U of A comma B less than or equal to max of A comma B. The product T norm T of A comma B is equal to AB, and then T conorm of S of A comma B is equal to minus A plus B minus AB, found to be most effective here. Now we discuss about the topic semantic segmentation. Semantic segmentation, let x is equal to r raised to I xa and y denote the output space and x denote the input space, means one of this image space. For semantic segmentation of 5 different scores, the 4 score in S, score 0, score 1, score 2, score 3, complemented by the background BG score assigns to the pixel that were not annotated for showing markers associated with the area of the class in S. As such, y is equal to set 0, 1, 2, 3, comma bg raised to I xa. The system need to learn a mapping omega from x to y. The model omega several network architecture for end-to-end image segmentation such as the UNet and more recently proposed UNet++. The semantic segmentation method help us to get a more accurate result. With the help of this background color, we can identify more accurately the COVID affected regions. Semantic segmentation instant compares pixel level classification of the pathological artifact within each frame. A pixel-wise categories cross entropy loss is adopted between the segmentation mask G of In and the model predictions Yn cap is equal to omega of h of xn. The function G and x are the pre-processing transformation applied prior to training. The data set is split into train 70% and test set 30% at a patient level. During training, we are given a training set of n image label pair t is equal to set xn comma yn up to n is equal to 1 to n is given where xn element of x and yn element of y. The model parameter are learned by backpropagating the earlier defined categorical cross entropy using Adam optimizer with a learning rate of 10 raised to minus 5. The training was if the following figure shows the four examples of B mode input image frames and annotation including the COVID-19 biomarkers, the corresponding semantic segmentation and contours of COVID-19 markers by deep learning. With the help of background color, we can identify the virus affected regions more accurately. The background colors are represented with the help of red colors and blue, etc. Now we go through this result analysis. In frame-based score prediction, in this paper we use a CNN plus regressor STN plus SORD, and then the average value of this methods has higher compared to another models. In this frame-based score prediction, we use three settings: one regular metrics to drop transition frames, three interdoctor agreement, and then in our model has higher average value 71.4 compared to another models. And this table shows an analysis of this proposed system for the frame-based prediction streams of F1 score. Now we discuss the result analysis of video-based score prediction. In video-based score prediction, we use uninorms. Then it has higher value. Mean, the table shows mean and standard deviation of weighted F1 score, precisions and recall. Now we discuss about result analysis of semantic segmentation. The table shows the segmentation performance of semantic segmentation method. A benefit of using ultrasound is a low risk of this cross infection when using a plastic disposable over and individually packed ultrasound gel on portable handle machine. It is a possible applications, and then LUS can be performed inside the patient rooms, making it a superior method of point of care assessment of patients. Ultrasound renders real-time images and combined with our DL methods provides result instantly. Low and middle income countries where diagnosis through RT-PCR or CT may not always available can particularly benefit from low cost ultrasound scanning. Future scope. In future, we demonstrate how transfer learning from deep learning models can be used to perform COVID-19 detection using images from the three most commonly used medical image modes: X-ray, ultrasound, and CT scan. It provides more accurate result. Conclusion. The replacement of traditional cross entropy with the SORD loss for the ordinal regression clearly improves the performance of the frame-based score prediction model. The video-based classification achieved F1 score of the 61%, a precision of 70%, and a recall of 60%. The segmentation model is able to discriminate between areas in B mode LUS images that contain background healthy markers and COVID-19